right, so we are going on in section 5.4. Let's do a quick little theorem. So theorem 5.17. And this theorem says that if A is orthogonally diagonalizable, then A is symmetric. Okay, so we want to prove this. So we're going to assume that A is orthogonally diagonalizable. And then our last line of our proof is going to be, thus, A is symmetric. Okay, so let's think about where this needs to go. So to get something that's symmetric, we need to have A transpose is equal to A. So that's where we want to get to. What do we get from orthogonally diagonalizable? So that means, thus, there is a matrix Q, an orthogonal matrix Q, and a diagonal matrix D such that Q transpose, Q inverse AQ equals D. But since Q is orthogonal, we have that Q inverse equals Q transpose. That was a theorem that we had from a previous section about orthogonal matrices. So Q transpose AQ is equal to D because Q inverse is Q transpose. So I can just replace Q inverse with Q transpose. So we have that QD Q transpose is equal to A, right? But then A transpose is equal to, well, A was QD Q transpose, and then we're going to use those theorems about the transpose. So what we'll have is it flips the order, remember? So I'll have Q transpose, and then D transpose, and then Q transpose. And so that gives me what? Well, Q transpose is just gets back to Q. D transpose is just D because it's a diagonal matrix. And then Q transpose I can just write as Q transpose. And what is that? Well, that's equal to A. So I end up with that A transpose over here is equal to A over here. So A transpose equals A, thus A is symmetric. And that's the end of our proof. So this gives us one direction. If we have a matrix that's orthogonally diagonalizable, then we get that A is symmetric. And so the spectral theorem is going to give us the opposite direction so that we get an if and only if statement. Let's do the next theorem. This is theorem 5.18. And that says that if A is a real symmetric matrix, then it has real eigenvalues. And by real, we mean as opposed to complex. By real here, we mean like real numbers, as opposed to complex numbers. Okay, so that's what we mean by real eigenvalues. Okay, so the proof of this is, I feel like you're going to get a little bit lost in this proof. So I'm just going to skip the proof of that, but there is a proof of that in the textbook that you can look over. And it uses a little bit of notation about the complex conjugate, and if a number is equal to its complex conjugate, then the number is a real number. So there are some of those ideas that go back to dealing with real and complex numbers that you may or may not remember from college algebra days or whenever you last dealt with real and complex numbers. Let's skip on to theorem 5.19, and then I'll give you the spectral theorem. And then we'll just do a few examples of orthogonally diagonalizing a matrix. So here's theorem 5.19. And that says that if A is a symmetric matrix, then any two eigenvectors are orthogonal. Okay, and the proof of that is not very long, but I'm going to skip it because I want to get to examples. Theorem 5.20 says, this is the spectral theorem. Okay, and this says let A be an n by n real matrix. And again, here real means that the entries of that matrix are real numbers. Then A is symmetric if and only if it is orthogonally diagonalizable. Okay, and so orthogonally diagonalizable means that there is a matrix made up of orthonormal vectors, and then we have a real entries along our diagonal of our diagonal matrix that are corresponding to the eigenvalues and so on. And so this is the if and only if. So if it's symmetric, it's orthogonally diagonalizable. If it's orthogonally diagonalizable, then it's symmetric. So it goes both directions. All right, so let's do an example. So we're going to orthogonally diagonalize the matrix. And we have 2, 1, 1, 1, 2, 1, 1, 1, 2. So again, you can see that this is a, you can see that symmetry there, that green triangle on the top corresponds to that triangle on the bottom, that there's a line of symmetric reflection across that diagonal. So you can see the symmetry of that matrix there. So the spectral theorem tells us that since this matrix is symmetric in this way, it's going to be orthogonally diagonalizable. So first thing we want to do is find the eigenvectors. The eigenvalues. So we're going to do 2 minus lambda and so that's going to give us 2 minus lambda. Oh gosh, this is going to be a big long thing here. This says that we already did this example. 5.17. Okay. Okay, so this is telling us the characteristic polynomial, blah, 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 is going to equal negative lambda cubed plus 6 lambda squared minus 9 lambda plus 4, which factors to negative lambda minus 4, and then lambda minus 1 squared. Okay. And so our eigenvalues are going to be lambda equals 4, lambda equals 1, and lambda equals 1 are our eigenvalues. Okay, and so now we can find the corresponding eigenvectors. So when lambda equals 4, what do we get? So 2 minus 4, negative 2, 1, 1. 1 minus 2, 1, 1, 1 minus 2. Okay, what am I missing here? Doesn't seem like that's gonna give us what we want. Okay, I'm just gonna do, let's see what happens if I row reduce this guy. I'm not seeing it immediately, but let's say I row reduce this guy. We're gonna say, let's do, multiply the second two rows by 2 so I can subtract them. 2 plus 1 is 3, and then I'll get 0. Okay. So it looks like I'm getting that. Okay, so I get some pivots here and here, and then my free variable is going to be this guy, and so then I'll get negative 2x1 plus x2 plus t equals 0, and then I'll get x2 minus t equals 0, and x3 is t. So x2 is also t. And so we have 2t minus 2t divided by minus 2. So x1 is also t. So my vector ends up being 1, 1, 1. Okay, is the eigenvector that corresponds with the eigenvalue with 4. Okay, so if lambda equals 1, then what will I get? 2 minus 1. I'll just get 1s all over the place. So that gives me 0s everywhere. And so my only pivot is here. So that means I have 2 free variables, s and t, here and here. And so I get that x1 plus s plus t equals 0. x2 is s and x3 is t, so x1 is equal to negative s minus t. And so I'm going to get the vectors, if I look at the coefficients of the s's, I'll get negative 1, 1, 0. And if I look at the coefficients of the t's, I'll get negative 1, 0, 1. So those are so that's saying that E1 is equal to the span of these guys here. And E4 is equal to the span of this guy. Okay, so those are my eigenvalues and corresponding eigenvectors. Now, are these eigenvectors already unit vectors? Okay, so the first one, so it looks like not. So let's look at this vector 1, 1, 1. So we want to make the eigenvectors into unit vectors. Oh, and we also want to check that they are orthogonal. So we can check that. So if I do 1, 1, 1 times negative 1, or dot with negative 1, 1, 0, I'm going to get negative 1 times 1, which is negative 1 plus 0. So that gives me 0. If I do this guy dot that guy, I'm going to get 0. If I do this guy dot that guy, I'm going to get Okay. Okay, hang on. The corresponding eigenspaces are this. Check this. Every vector in E4 is orthogonal to every vector in E1. Okay, so we got that. Okay, all right, so maybe they don't all have to be, okay, anyway, all right, so then let's make them into unit vectors. So I can do 1, 1, 1 times 1 over square root of 1 squared plus 1 squared plus 1 squared. So I get 1 over root 3, 1 over root 3, 1 over root 3. So that's the one corresponding to the lambda equals 4. And then the first one corresponding to lambda equals 1, I'm going to have 1 over square root of negative 1 squared plus 1 squared plus 0 squared times negative 1, 1, 0. So that gives me, that's going to be square root of 2. Okay, and then for lambda equals 1, the other one, I'll have square root of negative 1 squared plus 0 squared plus 1 squared times negative 1, 0, 1. So that's going to give me negative 1 over root 2, 0, 1 over root 2. So those are now I've made them into unit vectors. All right, so I think we're ready to write it all down. So, oh, shoot. Oh, yeah. Oh, God. Okay. Oh, all right. So what I didn't do is, shoot. Okay. So I was looking at this E1, and I was seeing that it was the span of these two vectors, but I noticed that they're not orthogonal to one another. So I actually do need to straighten them out. Oh, gosh. Okay. We need to straighten out the basis of E1 is not orthogonal. So we need to straighten it out using the Gram-Schmidt. Process. Oops, I spelled Gram wrong. I always want to stick in the extra letter there. I think it's G-R-A-M. Schmidt. Okay, so I need to straighten those out using Gram-Schmidt. Okay, so I'll take, well, I can pick whichever one I want. I'll just do the one the book does. So I'll pick negative 1, 1, 0. So I'll let me see what the notation is. Let me go back to the Gram-Schmidt notation just so that I don't confuse you. I think they called them V1. Okay, so we're going to say this guy is x1 and this guy is x2, just because that's the way the book did it. So I'm going to let x1 equal negative 1, 0, 1. So then I'm going to let v1 just be x1. And I'm going to say x2 is equal to negative 1, 1, 0. And so I want v2 to be equal to, v2 is going to be equal to x2 minus, and then I'm going to do v1 dot x2 over v1 dot v1 times v1. Okay, because I'm going to subtract off the part of x2 that is parallel or in the same direction as v1, and then what's left over will be perpendicular to it. So let's write this down. So x2 is negative 1, 1, 0. I want to subtract off from that. So v1 dot x2. So v1 is that dot x2. So I'm just going to get 1 plus 0 over v1 dot v1 is going to be 1 plus 1, so 2. And then v1, again, is negative 1, 0, 1. So I'm going to get, so if I add that all up, I'll get that my v2 is negative 1 plus a half. So it'll be negative 1/2. And then 1 minus 0, and then 0 minus a half. Oh, shoot. Sorry, it was 1 minus 0. So 1 minus 0 is 1, and then 0 minus a half is negative 1/2. So this now I have a basis. Now this guy and this guy are a new basis for E1 that are actually perpendicular to one another, and then now I can normalize them. Okay, so see, this kind of brings together so many things that we've done all semester. So we've got to kind of go back and remember. Okay, so then this guy, negative 1, 0, 1, I need to multiply by 1 over the magnitude. So it's going to be square root of 2. So I get negative 1 over root 2, 0, 1 over root 2. And then for this guy, I want to make it normalized. So I want to do 1 over square root of, oh gosh, we're going to have 1/4 plus 1 plus 1/4. So it's going to be negative 1/2 times, oh gosh, let's see, square root of 1.5. So it's going to be 1 over 2 square root of 1.5. There's probably a better way to write that. But anyway. Okay, and then we'll have 1 over square root of 1.5, and then minus 1 over 2 square root of 1.5. So there you go. Let's see. The book probably writes that in a better way, where it looks like it's not so crazy. They're calling that... Okay, hang on. Let me make sure. They have square root of 6. So if I put that 2 inside there, it would be a 4. So 1.5 times 4 is square root of 6. Okay, yeah, so that's equal. So I'm going to have 1 over square root of 6. So if I put that 2 underneath that radical, it becomes a 4. So that's where I get that. This is 1 over, well, I could say it as 2 over square root of 6. And then negative 1 over square root of 6. So that's how it's written in the textbook. That's fine. That's probably better notation than square root of 1.5. So, okay, whatever. And so now I'm ready. I've got my Q. My Q, I'm just going to put all those vectors in there. So the normalized version. So 1 over root 3, 1 over root 3, 1 over root 3. And then I could do the next one. Negative 1 over root 2, 0, 1 over root 2. And then I have negative 1 over root 6, 2 over root 6, negative 1 over root 6. And this guy is my Q. And then my D that corresponds to that is going to be, it needs to make sure it corresponds to those eigenvectors. So that one with the 1 over root 3's, that corresponded to lambda equals 4. So I'll have 4, 0, 0, 0, 1, 0, 0, 0, 1. The other two correspond to the eigenvalue 1. So there's my Q and there's my D. And so that is that. Okay, there's one more little thing, and this is based on all of this, there's another way to kind of write the spectral theorem, and this is called the spectral decomposition. It's basically the same thing as just a slightly different notation. And so that is saying I can write this A as equal to lambda 1 times Q1 times Q1 transpose plus lambda 2 times Q2 times Q2 transpose plus dot 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 plus lambda n times Q n times Q n transpose. And so that's just another way of writing these out. And so again, this is my lambda 1, this is my lambda 2, this is my lambda 3, and so on. This is my Q1, Q2, Q3, these column vectors. And so I can write down my A as lambda 1, which is 4, Q1, which would be 1 over root 3, 1 over root 3, 1 over root 3, times Q1 transpose, which would be 1 over root 3, 1 over root 3, 1 over root 3, plus lambda 2 is 1 times Q2, which is negative 1 over root 2, 0, 1 over root 2. And then I could do that thing transpose. Plus the next one, lambda 3 is 1, and then I have Q3. And then that thing transpose. And you'll see that when you do all of this matrix multiplication, again, like this is what? This is a 3 by 1, and this is a 1 by 3. You'll end up with a 3 by 3 matrix here. And when you add all of that up, you'll end up getting back to the matrix A. So it's just another way to write down the decomposition of this matrix, this diagonal matrix, in terms of these unit vectors that are orthogonal, that create a basis for the eigenspace. Okay.